which is going to be estimated positions. We're going to go ahead and do problem number 1 on the chart. And so our answer in each case is going to be to plot the estimated position. So we'll find where we are and to state the speed made good for each problem. Now, the nice thing about the problem set is they've given us a table. Later on, you might get a word problem. But for now, the data is presented in an easy to access format, and it's presented in the order that you should use the data. So if you're ever stuck, just look at the next box, and it should instruct you what step comes next. So for section C, question number 1, our start position is going to be 29 degrees and 30 minutes south, 31 degrees and 15 minutes east. Hopefully you're getting used to the latitude and longitude scale here, but 29 degrees is going to be anything above the 30 on the chart, and 29 degrees, 30 minutes will specifically be this line of latitude. 31 degrees will be here, 31 degrees and 15 minutes east will be this point. And conveniently for us in this problem, we already have an existing line of latitude and longitude that meet at that location. So right here will be our start point. Now, there's no official symbol for that point here. I'm just going to go ahead and put the time that I was at that position, and our start time was 0900 for this example. From that point, we're given a ship's heading. So this is the direction that the ship is facing, and we're going to be steering somewhere away from the coast here for this problem, and that's given to us in degrees compass. So the first step in this problem, probably on some scrap paper where you can keep your work neat, will be to convert that into degrees true before we plot it on the chart. So we'll set up our table, TV, MDC. Okay, normally we would add whiskey, but we're going to be working from compass back to true in this case, so we'll be subtracting west. And the compass value given is 150 degrees C. Page 4 of your problem set is this deviation card. With this value, 150 compass, we'll enter the ship's heading column. Look for the value closest to 150. Coincidentally for this problem, the deviation is 0. If it were a west value, we would subtract, an east value we'd add. But for this problem, we don't really have to make an adjustment, so magnetic is 150. Back up at the top of the problem set, again, they've given us the variation. So for all problems in this problem set, we can assume that that's going to be 25 degrees west. 150 minus 25, again, not a bad idea to work on the calculator, but that's going to be 125 degrees true. So that's the line I can draw on the chart. So I'm going to switch over to my pencil. We'll go ahead and grab our parallel rules, and we're going to find 125 on the compass rose. Again, be precise. We'll line up the edge of the rule and 125 on the outer edge of the on the outer edge of the true bearings for our compass rose. Slide up to that start point, and this is going to be a nice short line. The next piece of data that they're going to give us in the problem set is going to be leeway. You don't necessarily have to do this, but a southwest wind is coming from the southwest, pushing us to the northeast. So I like to draw a little line there representing the wind, and the leeway is 6 degrees. And again, that's not a direction that you're going to find on the compass. Instead, it's going to be an adjustment to that original ship's heading. So this was a ship's heading of 125, but the wind is pushing us 6 degrees in this direction. So from 125, I'm going to make a adjustment, 1, 2, 3, 4, 5, 6 spaces to 119. And again, I'd rather not think about that as addition or subtraction. It's just a being pushed in that direction relatively. And having measured that, we'll come up to our start position. And we're going to draw that in as a longer line. Now this is our path through water. This is the ship's water track. That's going to get 1 arrow for notation. And on that line, we can next measure the boat speed. Again, working left to right, having dealt with leeway, the next value they give us is boat speed. Now, if you always work in 1 hour time increments, you don't need to worry too much about this math. But we've got the equation distance equals speed times time. For this problem, our distance is going to be equal to our boat speed, which is 6 nautical miles per hour, or 6 knots, times the 1 hour time increment that we're working on. Again, if you can do this in your head without making a mistake, I'm not too worried about it, but that's going to be a distance equal to 6 nautical miles. That's how far a boat would travel through the water in that time interval. So over on our latitude scale, I'm looking for a 6 nautical mile distance. So I'm going to start with an existing line like 45. The direct distance between 45 and 40 would be 5 miles. Measure 1 extra minute beyond that. That should be about 6 miles there. You can do that starting here as well. Just go ahead and make sure you've got 6 minutes. We'll go ahead and place one arm of the divider at the start position and the other on the water track. This is just going to get a hash mark. That's our distance run, or our dead reckoning position on the water track. And absent any water movement, that's the position we would be at. The last step in this problem is going to be to consider the current. And for this problem, the current set is 0, 0, 0 degrees. That doesn't mean there is no current. That is a compass direction, yeah. That is true north, straight north. And the current is pushing us at a rate of 2 knots. So coming back to our compass rose and finding north from the middle of the compass rose up, there's 0, 0, 0. We're going to transfer a parallel line from that, starting at our dead reckoning position and working up to the north. That's the current vector, effect of the current on the vessel. So we're going to give that 3 arrows. And then the current's pushing at 2 knots. So again, distance is equal to speed times time. Current's pushing at 2 nautical miles per hour for 1 hour. You can do it in your head, no worries. It's going to push you 2 nautical miles. Again, anywhere on that latitude scale, we're going to go ahead and measure out 2 miles. That's how far the current's pushed us in that same time. Those dividers can be a bit sticky, so be precise with them as well. We're going to go ahead and measure that distance up the current vector. It's like coincidentally, I drew that pretty well. And I'm going to go ahead and put a dot there, and I'm going to go ahead and put a triangle around that. Now, our start time in the problem set was 0900. They wanted to know our position at 1000, and that right there is our 10 o'clock position. That's pretty much the hard work done. However, the boat and the current were not moving us at separate times. So the final step for this problem is going to be to go ahead and connect our start position and estimated position. This is the path the boat actually takes. So we're going to call that our ground track. And just as a heads up, this is where I'd be after 1 hour. But if I needed to know where I was after 2 hours, I could just make this twice as long, as I might need to in the next problem. Ground track gets 2 arrows, 2 feet on the ground, ground track. And that's my plot done. So they've asked me to plot the estimated position. That's done, but they've also asked me for the speed made good. Now our water track represents our boat speed. Our current represents the current rate. So the speed made good must come from the only remaining line here, which is the ground track. So the last step for this problem might be to go ahead and accurately measure out this distance here. Bring that to our latitude scale. Measure out what that comes to. It looks like it's coming out to about 5.3, 5.4 nautical miles. I believe the answer key says 5.3. You got a little bit of leeway there. My work looks like 5.4. And technically what I've just done is I've measured a distance. So the distance along that ground track is equal to 5.4 nautical miles. Again, if you can do this work in your head, you'd be good to go. But what I need is a speed made good. Distance divided by time should give me speed. And if I do 5.4 nautical miles divided by 1 hour, since that's how long it took me to get there, well, then my speed is going to be 5.4 knots, or nautical miles per hour. So that is my speed made good.